Hi everyone, my name is Max Vancil,
I'm Ronnie Matteini.
and today we are going to go over a bit about the history of computer vision and autonomous vehicles for ECE 4881 Robot Vision out of University of Michigan Dearborn.
Alright, so let's get going. We would like first to go over exactly what autonomy means in regards to automobiles. There are 6 levels of autonomy in today's world, scaling from a level 0 to 5. We start with a human driver monitoring all driving environments. As we move to level 1, a driver assist system is in place, which is either steering or acceleration assist. Level 2 incorporates both steering and accelerating assist while keeping the driver still in charge of the vehicle. Level 3 has multiple ADAS systems in place where it performs all driving, however, the human must intervene when needed or necessary. As moving to high automation or level 4, a driver could expect much less human intervention as ADAS systems should know what to do to respond to a driving situation. Lastly, we have a level 5 or full automation. This is where human intervention is not needed and where all of the large automobile companies are trying to get to today, a fully autonomous vehicle.
As early as the 16th century, artist and inventor Leonardo da Vinci was contemplating the idea of an autonomous land vehicle. In 1500, da Vinci designed what many considered to be the first robot, a cart that relied on high-tension springs to be powered along a predetermined path by means of a steering being programmed at preset angles. This idea, which can be considered to be a precursor to the modern autonomous vehicles of today.
The Stanford cart was originally designed by Stanford engineering graduate student James Adams in 1961. Adams's goal was to study how feasible it would be to control a moon rover from Earth. This version of the cart was comprised of 4 bicycle wheels, electric motors, and a TV camera. After various tests, Adams concluded that the communication delay that existed with the steering commands made this design impractical, since the cart could not be properly controlled at speeds greater than 0.2 miles per hour. Little that Adams knew, his moon rover experiment would prove to yield the first true autonomous wheeled vehicle in just a few years later.
In 1963, graduate student Paul Brasted added an analog computer to the cart. This early computer improved the controllability of the cart by removing some of the communication delay previously discovered by Adams. This new scheme will consider future steering commands in future cart locations, and it did improve the speed at which the cart could be operated at, from 0.2 to 5 miles per hour. Further building on Adams' original design, executive officer of the Stanford Artificial Intelligence Laboratory, SAIL, Lester Ernest, modified the cart to navigate along a small road that surrounded the SAIL building. Due to the robust size of computers of the day, Lester and his colleague Rodney Schmidt accomplished this by transmitting the TV images to the SAIL computer, and from here a separate radio link was then used to send the control commands from the computer to the cart. Ultimately, Professor John McCarthy began working on the cart and modified it once again. With this version, no operator controlling the cart was needed, with the cart being programmed to follow a solid white line. At this stage in its lifespan, the cart became the world's first autonomous vehicle. In the late 70s, the cart again changed hands and was worked on by Hans Moravec and Victor Scheinman. The two modified the camera's mounting apparatus, which now allowed the camera to slide back and forth, greatly increasing the car's optical view. The main advantage with this modification was now the cart could remain stationary and multiple camera views could be achieved. As computer technology improved, so did the cart's performance. Relying on one of the most powerful mainframe computers of their day, the PDP-10, the computer's KL-10 processor was used to control a multi-ocular vision system that enabled the cart to successfully navigate a crowded classroom filled with chairs without human control. This task, which would have been considered impossible just a decade earlier, took approximately 5 hours to complete.
As digital image processing developed in the 1970s, this allowed for greater innovation in the area of computer vision. Research in many areas of computer vision took place and new algorithms were developed, such as pictorial structures, optical flow, and line labeling algorithms. By 1977, the Tsukubu Mechanical was yet another milestone in autonomous vehicle driving. This Japanese-based mechanical engineering lab produced an autonomous passenger vehicle that used analog computers and two mounted cameras to detect and recognize white street markings. This vehicle, which is considered to be the first world's autonomous car, could reach speeds of 20 miles per hour. In the 1980s, quantitative image and scene analysis gave way for improvement on the Tsukubu Mechanical. In 1986, the Pan-European Prometheus project began. Lasting until 1994, the Prometheus project remains the largest autonomous vehicle project ever funded. This project consisted of 12 demonstrated projects ranging from vision enhancement to collision avoidance. Also, in 1986, a German engineer, Ernst Dickmanns, and his team from the University of Bundeswehr, Munich, retrofitted a regular sedan with an array of cameras and 60 microprocessing modules. Relying on saccadic vision, Kalman filters, and parallel computers, Dickman's system could detect objects on the road, both behind and in front of the vehicle. He called his system Vamors and said that the most important object of his project was dynamic vision. His imaging system was able to filter out noise and focus only on the object it was meant to focus on, exactly like a Gaussian filter. The Vamors proved to be very successful as it maneuvered Germany's Autobahn at a high speed of 60 miles per hour. As research and development in computer vision continued, the 21st century brought new feature-based recognition and interactive tone mapping algorithms. In order to further technological development and spark innovation in the autonomous vehicle field, in 2004, the Defense Advanced Research Projects Agency, or DARPA, funded the DARPA Grand Challenge. Since then, the challenge has taken place annually with a cash prize being awarded to the winner. In the inaugural year, the challenge required an autonomous vehicle complete a 150-mile route in the Mojave Desert, with the best car reaching 7.32 miles. No car completed the race. The following year, out of 23 contestants, all but one failed to reach the previous year's best of 7.23 miles, with 5 vehicles completing the entire race. Since then, the competition has evolved. In 2007, the Urban Challenge was held. This took place in a simulated urban environment and required vehicles to obey traffic regulations and successfully interact with other vehicles and obstacles. In just 1 year, the DARPA Grand Challenge achieved its goal of innovation in the field of autonomous vehicles.
One of the most interesting and intriguing systems today is Tesla's autopilot. This semi-autonomous feature enabled drivers the option to drive hands-free on large highway and freeway systems. With the use of only 8 cameras, 12 ultrasonic sensors, and one forward-facing ARS or advanced radar system, Tesla developed the software to drive their vehicles hands-free. Many people don't realize that Tesla is still in the developmental phase of producing fully autonomous vehicles, and what they currently have is only semi-autonomous software. Tesla has needed to increase their processing power with over 40 times the computing power of their previous generations. This has enabled them to run their vision, sonar, and radar systems simultaneously for safer semi-autonomous driving. With the given hardware on their vehicles, Tesla is able to drive completely autonomously. However, their software lags behind. Tesla is currently creating software for their vehicles to drive fully autonomous, which can be flashed onto the vehicle hardware over the air.
AutoX is a small company founded by former Princeton professor Jianjing Zhao. Dr. Zhao and his team have created a computer vision system that relies totally on cameras. Unlike Tesla and Google, AutoX's design does not have radar, LiDAR, or ultrasonic sensors. AutoX has retrofitted a Lincoln MKZ with 7 $50 Best Buy cameras, and they have successfully tested their design. AutoX's goal is to provide this technology to just about everyone, and they plan to add LiDAR to its design once it's more affordable. AutoX does not plan on producing a vehicle from scratch, but they do intend to supply automakers with the proper software needed to achieve this affordable autonomous system.
The major issue autonomous systems face is reacting correctly to everyday hazards drivers experience. The University of Michigan is currently aiming to recreate the chaos one would experience while driving through a busy urban environment. M-City is a 32-acre simulation of roadways located in Ann Arbor, Michigan. Costing upwards of $10 million, the Fox City is comprised of movable building facades, various road signs, and multiple types of road types. The sole purpose of this recreation is to give the developers of these autonomous systems the opportunity to study how these systems would operate in a real-world environment.
Today, modern autonomous systems are comprised of various types of technology all working in unison. These include various sensors such as radar, LiDAR, and ultrasonic. These sensors are tasked with monitoring nearby vehicle positions, detecting the edges of roads and lane markings, and curb and vehicle detection while parking. Along with these sensors, strategically placed video cameras are used to detect traffic lights, signs, pedestrians, and other vehicles. These sensors and cameras feed all this data to a central computer. This computer processes all of the data and can use it to regulate speed, braking, and steering of the vehicle.
Today, NVIDIA is leading the way in autonomous vehicle hardware. In 2016, they released the NVIDIA Drive PX2, and current Tesla vehicles contain this powerful hardware technology. The NVIDIA Drive PX2 allows the automotive industry to use artificial intelligence to tackle the complexities inherent in autonomous driving. It utilizes deep learning on their most advanced GPUs for 360-degree situational awareness around the car to determine precisely where the car is and to compute a safe, comfortable trajectory. In September of 2016, NVIDIA announced the newest of the Tegra processors, the Xavier. Xavier is an AI supercomputer designed for the future of autonomous vehicles. It is 50% more powerful than the Drive PX2. The Xavier will be available to automakers, Tier 1 suppliers, startups, and research facilities in late 2017.
That will conclude our presentation. Thank you guys for joining us. Nice one.